So what happens when I have my PowerPoint on and also my camera? Can you guys switch between the two of them, or do I have to close one so you can see the other?
We can switch between them, but it does require a right click on show participants, I believe. Or sorry, not
A
that.
right click by who? By you or by me?
By us, and it's not a right click. Sorry, it's more actions.
Well, let me see what happens. I'll share my PowerPoint, and then you guys can.
Actually, I was able to switch between cameras by just clicking on the at the bottom where it shows all the faces and stuff. Just click on that, and then it made the document camera bigger.
I think for the video recording, however, it defaults to the PowerPoint. So from last session when you were writing on the document camera, we couldn't see it, or it was in like a small screen on the side.
Oh, really? We don't want that, especially today, because what I'm doing on the document camera is big. Why don't I see my...
Yeah, that's interesting because in last week's lecture, we could see the notepad towards the end when you were doing your sketches, but towards the beginning, like Nico said, it was towards the bottom.
Yeah. I'm going to close a whole bunch of windows because it's too hard to find stuff. What I want. Let's see, I can close all this stuff. Okay, this should do it. Okay, so maybe you can see my PowerPoint now.
Correct. And then the
Is it
sketch
true?
pad at the bottom right now.
Can you make it large?
The sketchpad, yes, you can. I think at that point I can toggle between the PowerPoint and the sketchpad. So yeah, I think I would have to click on the sketchpad if both are active.
Okay, so, but what I'm hearing is I need to not share this PowerPoint so that the recording can pick up the document camera, right?
I think so, yes, but I can also click at the bottom right to make the document as a main video, window. Either would work, I think.
Okay. Well, right now you should just see the document camera because I've stopped sharing the PowerPoint.
Correct.
Okay. Okay, so it's time to start. And I will. So I just want to use my document camera for a minute to talk a little bit more about this close packed structure. So you have to let me know if it's hard to see what I'm doing, because I only see the small view of my document camera while I'm talking about it. So there's a really nice way to look at these close packed structures, and that's by viewing what's called a 1-1-0 projection. So what it means is you put your eyes and you look at the structure from this direction. And these planes of atoms that you see like this, those are 1-1-0 planes. And why they're called 1-1-0 planes is not important to us at this time. If you take solid state physics, you'll learn why that's the case. But anyway, the point is when you look in this direction, all the A atoms lie right behind each other, and all the B atoms lie right behind each other, and all the C atoms lie right behind each other. Okay? And if you say that the A sites have coordinates 0, 0, 0, they're in the plane of the paper. And then the B sites, we learned the fractional atomic coordinates were 1/3, 2/3. If we say the B sites are up off the paper a little bit by 1/3 of the unit cell height, and the C sites are 2/3, 1/3, and we say they're up even further, then you can draw what the unit cell looks like in a 1-1-0 projection. You're looking in from this direction. The A atoms are at the bottom. The B atoms are shifted over, and they're up 1/3 of the unit cell along the Z direction. And then the C atoms are up 2/3, and they're shifted over again. It goes A, B, C, and then back to A along that line. So this is what a structure would look like that has a layer of A atoms, a layer of B atoms, a layer of C atoms, and a layer of A atoms. Any questions about that? Okay, so now I'm going to share my screen again. So I want to start talking about titanium disulfide. And titanium disulfide takes the exact same structure as lithium cobalt oxide without lithium. And this structure is called O1 for reasons that I'll explain later. So if it's titanium sulfide, the titaniums are these small balls and the sulfurs are these bigger ones. And if it's cobalt dioxide, the cobalt would be the small balls and the oxygen would be the big ones, okay? So I want to explain this structure in the notation of hexagonal close packed planes. So I want to talk about, when I say discuss on the board, there is no board, it's my document camera. So I want to talk about the lattice constants, what the atoms are in the unit cell, and where can the lithium atoms go. And then once we have the basic positions of the atoms and that sort of thing, we can use a computer program called Vesta to make a nice structure diagram that we can rotate and take a look at and so forth. So all of you will learn how to use Vesta in homework 1. So I'm going to go back to my document camera again and just draw a few things. Okay, so I'm going to draw the titanium layer in titanium sulfide first. It's very simple. It's just a close packed layer of atoms. Whoops, I messed it up. Start again. It's just a close packed layer of atoms. Like this. Continues forever. And it has what are called lattice constants that describe the size, the spacing between these dots. These are at 120 degrees from one another, and they each have the same length, called A. Can you see that okay?
Yeah, now it's good.
Okay, there we go. You guys got to tell me when you can't see anything. So for titanium disulfide, A is equal to 3.41 angstroms. All right.
Excuse me, I can't see anything.
You have to say that again.
Yeah.
I cannot hear you. Okay.
Do you hear us something? I only see the.
I cannot understand what you're saying.
Excuse me.
I think she means that because the PowerPoint is still on the big screen, like if you click on your little avatar, then we can see that document camera, but I don't know how it's in the recording now. Is the recording going to record your PowerPoint or what you're drawing?
I'm surprised the PowerPoint is showing because I've stopped sharing.
Yeah, the PowerPoint right now it's towards the bottom right corner. But I think you just closed it now. So now the notepad is still up. Yeah.
Okay, so there should be no PowerPoint now. Is that correct?
Yes.
Thank you. I see. Thank you.
Okay, good. So the question is, what does the 110 projection look like for titanium disulfide? Okay. So what we're going to say is that the titanium atoms are on the A sites, and we'll draw this 110 projection. So I'm drawing the unit cell box in the 110 projection. The titanium atoms are here on the corners. And these are the A sites. The B sites lie along a line like this. And the C sites lie along a line like this. So there's a sulfur atom here and a sulfur atom here in the neighboring unit cell. And we generally draw a line connecting these together. So there will be a sulfur atom here and a sulfur atom here. And then there's nothing in the van der Waals gap, which is in the middle. And then you have sulfur atoms here and here, and sulfur atoms here and here. So if you want to describe this structure, you would say it goes, this layer is a C, this layer is an A, and that's where titanium is. And I use a capital letter for sulfur or oxygen, and a small letter for the transition metal. And this one is B. And then there's nothing. This is where lithium can go. And then it goes C, A, B, and repeats. So that's the way a titanium disulfide structure is made up. So if you wanted to know the atom positions here, it would be the titanium. It's at, we'll call this 0. So it's at 0, 0, 0. It's on the A site. And then sulfur, the first sulfur here is on the B site, which is 1/3, 2/3. And how far is it up before the repeating cell? It's 1/4, 1/2, 3/4. So it's at 1/3, 2/3, 1/4. And then the other sulfur atom is up here on the C site at 2/3, 1/3, 3/4.
Sir, could you just raise the page a bit? Thank you.
Yeah, I only have a tiny, tiny view of what I'm drawing, and plus it's reversed. It's mirrored on my screen. If you learn about Microsoft Teams, they'll tell you what you see is mirrored compared to what the students see. The students see the right thing, and I see it mirrored, so it's not the greatest. So if you then were to use the structure visualization software, this is all you need to give it, is the atom positions and the unit cell vectors. So the A is 3.41, and this distance in real life is about 5.6 angstroms. Okay, so then we have to figure out, where can the lithium atoms fit in here? Where would they fit in this layer in between? Well, there's a couple of places that are the most attractive for the lithium to sit. If we put a lithium atom here on the A site, then when you look at it, you can say there's no sulfur directly above or directly below. So a lithium atom placed here would be what we call in an octahedral site. And I want to draw the octahedral site for you on another piece of paper. So the octahedral site would look sort of like this. I'm drawing in perspective view now. Those are 3 atoms, say from the C layer, which would be on top. And then we have to draw 3 atoms from the B layer, which would be below. And then if you join these atoms with lines, you'll find you get an 8-sided figure, which is an octahedron. And the lithium atom sits in the middle on the A site. And the position of lithium we designate with Greek letters. Okay, so lithium would be alpha, which is Greek for the letter A. So this is sulfur, lithium, sulfur. Now, there's another place that lithium atoms can go, and it's called a tetrahedral site. So a tetrahedral site would be a situation where you might have the sulfur on the A site, and down below, sulfurs are on a B sites. And then you put the lithium right below the sulfur above. Also on an A site. Okay. So there are one octahedral site for every titanium atom in the TiS2 structure, or per formula unit. And there are two tetrahedral sites per formula unit. Okay. And it turns out that lithium TiS2 has octahedral sites filled. But you can also, if you continue adding lithium to the material, you can make lithium-2 TiS2. And what you learn is that in this case, the two tetrahedral sites are filled.
So, Professor, when you keep adding lithium, are the lithium ions are going to migrate from the O site to the T site?
Yes, they empty from the O sites and they fill the T sites when you add so much lithium as this.
Okay, thanks.
This is the same structure is also found in lithium-2 nickel dioxide. Okay, so people that work on lithium nickel oxide and related materials may not even know that it can accommodate 2 lithiums per formula unit, but it can, okay, at low voltage, around 1.8 volts. It can form lithium-2 nickel oxide. So if you wanted to write down the structure of lithium TiS2 in the notation of hexagonal close packed planes, you would write it like this. You could start with a sulfur atom, and then you'd have a titanium. So you might go C, A, B, and then the lithium is on the alpha site. And then you repeat C, A, B, alpha. Sulfur, titanium, sulfur, lithium. And this structure is called O1. Why? Because the repeating unit just has one sulfur, titanium, sulfur slab. That's where the 1 comes from. And the O means the lithium in octahedral sites. Okay. So I want to now go to my computer for a minute and try to share my screen to show you something else. Can you see
Yes,
a
we can see
program
that.
called Vesta?
Yes.
Okay, so this is a program that you'll use in your homework that allows you to make nice structure diagrams of materials. And what's nice is you can rotate and take a look at what you've made, okay? So this is titanium sulfide or O1 cobalt dioxide. And when you rotate it like this, you're in the 110 projection. And you see the A site, the B sites, and the C sites, and then back to the A sites again, right? So it's a really handy way of describing structure. You know, if you just look at that, like that, you say, well, what the heck? What have I got? Hard to say, right? If you look down from above, you can see the triangular lattices that make up each close packed layer. So this is a really great software. You know, when I was a graduate student, these type of softwares did not exist. So we had to understand structure, you know, by drawing things on the paper like I've been doing. Okay, so now I want to move on and talk about lithium cobalt dioxide. And I'll do that first, just because I'm here to show you what it looks like in this Vesta. So here the oxygens are these big balls, which I think are red. Cobalt is the black, and the lithium is this smaller one here. And again, we can rotate this around and look at it. But when you look at this structure, it's often hard to get it back to the perpendicular direction. Mousing around is a little difficult sometimes. Okay, I'm coming into the 110 projection. Here I am. So this is different than titanium sulfide. Look, here you have a cobalt. The next cobalt is not directly above like it was in titanium sulfide. It's shifted over. So if this cobalt is on A, the next one up is on B. And the next one up is on C. And then it goes back again, back to the A site. So it's like each of these layers shifts slightly to the right as you go up the structure. The lithium is in octahedral sites again, and it's a 3-layer repeat. So this is called the O3 structure. So lithium cobalt oxide is O3. Okay. So we'll talk about exactly how you write down this structure in the notation of close packed planes in a minute. But I just wanted to show you what it looked like before I'll go back to the PowerPoint. Also, this software is nice because you can view the structure like this, and then you really see these lines that I draw between the oxygen, the transition metal, and the oxygen. You see these lines that I like to draw. Okay, so I'm going to go back to the PowerPoint now. I believe you should not see Vesta anymore. Is that true?
Yep. Yes.
Okay, so I'm going to go back to the PowerPoint. I think you should see the PowerPoint again. Is that true?
Yep.
Okay. Yeah, so this is the 110 projection of TIS2, which we talked about. We said C, A, B, empty space for lithium, C, A, B. This is a top view just showing you what the 110 plane is. When you have a view angle from the bottom looking up, all the titaniums lie along a row. And this set of sulfur lie along a row and so forth. And this slide shows you where the octahedral sites are and where the tetrahedral sites are in between the layers where the lithium can go. And this is lithium cobalt oxide, like I mentioned. Okay, so now I want to talk about what the O3 structure is. If we look at this from the bottom, and we have a 110 projection slightly tilted here, if this cobalt is A, this oxygen is B, this lithium is C. This oxygen is A, this cobalt is B, this oxygen is C. This lithium is A, it's on the line. This oxygen is B, and this cobalt is C. So I just went A, B, C, A, B, C, A, B, C, A, B, C. The structure is just A, B, C, A, B, C, A, B, C, A, B, C, A, B, C. And you just put in the right atoms in the right place. So I'll do that on the document camera. Okay, the PowerPoint should now be gone. Is that correct?
Yep.
And all you should see is my paper. Is that correct?
Yes, thank you.
Okay, I'm always making sure because I don't know what you see. So it may seem a little bit redundant and repetitive, but I want to make sure that you see what I think you see. Okay, so now I'm going to draw the structure of lithium cobalt oxide in the notation of in you know what I've been showing you. Where do I want to go? That way. 6. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is the unit cell, okay? And our A sites are going to be on this line, B, C, back to A. And then we'll start. We'll put a cobalt on A, and like I said, the next oxygen comes on B. And there would have been one on C down here. And then the lithium is on C. And then we go back, oxygen on A, cobalt on B, oxygen on C. That means lithium will be on A, oxygen on B, cobalt on C, oxygen on A, lithium on B, and then oxygen on C, cobalt back on A again. We're back to the starting point. So that's what O3 lithium cobalt oxide looks like. And if you want to use the VESTA program and you don't know anything at all about something called space groups, which some of you will know nothing about space groups, and you want to use VESTA, you have to tell it where the atoms are. So I'm going to tell you where the atoms are now. So at the bottom, we have the A site, that's 0, 0. We'll make this 0 in the vertical direction. So that's cobalt. And then we have oxygen, it's on B. That's 1/3, 2/3, and it's up. How far? Well, you would have listened to me count to see how many points of the page to go up. This is 1/12 up compared to the total repeating unit. 1/12 oxygen. And then we have lithium on the C site, which is 2/3, 1/3, and it's up 2/12, which is a 1/6. Then we have oxygen, it's at 0, 0, and 3/12 is a quarter oxygen. Then we have lithium at 1/3, 2/3, 4/12 is a 1/3. That's cobalt. And we have oxygen at 2/3, 1/3, 5/12. Lithium is on the A site, that's 0, 0, 6/12 is a half, and so on, right? I may as well fill them in. 1/3, 2/3, 7/12 oxygen, 2/3, 1/3, 8/12 is 2/3 cobalt, 0, 0, 9/12 is 3/4 oxygen, and then 1/3, 2/3, and 10/12 is 5/6 is lithium. And then finally we have a C site, 2/3, 1/3, and 11/12 is where the oxygen is. And then we're back to the beginning. So the way this is stacked is cobalt should be a small letter. We always make our transition metal small. A, B, C for lithium is gamma. Always lithium is a Greek letter. Then the oxygen is A, cobalt B, oxygen C. Lithium is on the A site, that's alpha. Big B for sulfur, for oxygen, sorry. Small c for cobalt. Big A for oxygen. Beta for lithium. And big C for oxygen, and then back to A for cobalt. So this is the repeating unit. And if somebody like me gives you a stacking sequence like this on a homework problem, you should be able to draw the structure in what it looks like here. Okay, any questions about this? Okay, well, it turns out that lithium cobalt oxide can have another structure. It's different than this. And in the 1990s, it was interesting to figure out which one of these two would be more interesting to use in lithium-ion cells. And you can make this alternative structure for NMC or NCA or anything you want. But it's harder to make. It's more expensive to make. And if its properties were significantly better than O3, people might do it. But the properties are not better, so people don't do it. But no one knew this at the beginning. So it's important to understand what this is. So this is O2 structure, lithium cobalt oxide, okay? So this means it has two cobalt oxygen slabs in the unit cell, and the lithium is octahedrally coordinated. And what does it look like? Well, we'll draw it. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we start with cobalt on the A site. And we have oxygen on B. We have oxygen on C. Like that. The lithium is in this layer, and it turns out to be on a C site. So that's where the lithium is. And then the oxygens go like this. They're on A. So this is an octahedral site for lithium because there's no oxygen above or below. If the oxygen was either above or below, it would be a tetrahedral site. And then we have to have a two-layer repeat. And the only way to do that, it turns out, is to put the cobalt here, and the next oxygen there. So this layer is if you like, it's in the, it's, you know, these lines that join oxygen, cobalt, oxygen is tilted in the other direction. This layer is actually rotated relative to the layer stacking in O3 lithium cobalt oxide. Then the lithium goes on the A sites, and you go back to where you started from. Okay. So the stacking here goes C, A, B, gamma, A, B, whoops, A, C, sorry, C, B, alpha, C, A, B. And it's different than O3, right?
Hi, Jeff.
Yeah.
Can you put the two structures next to each other just on the screen to make a comparison? Is this okay?
We can try.
Okay, thank you.
Whoops. Can you see them both now?
Yep.
Yes, thank you.
Okay. So I'll go back to the Vesta program to show you what O2 looks like in Vesta. So now you should be able to see the structure of O2 here. And for sure, you can see what I'm saying, you know, the little line that I like to draw between the oxygen, transition metal oxygen, here it's up and to the right. But in this layer, it's up and to the left. So it's unlike the O3 structure. And the voltage versus lithium content curve for O2 and O3, they're different. And they should be different because they're different materials. And it's really quite cool. And we'll see that later on in the class, how the structure affects the voltage curve. Okay, so now I want to go back and do one more thing with the PowerPoint. So the Vesta should be gone. Now I'll put the PowerPoint back on. And we talked about O2. Yeah. If you try to draw another O2 structure, you know, that does not have this intermediate layer with the layers, if you like, in the opposite direction, you can't do it. The middle layer has to be backwards to have an O2 structure. I suppose it's worth just showing you what I mean. So somewhere I have a diagram like that. Where is it? Here we go. So I'm not going to draw this, I'll just show it to you on the document camera. So let me get rid of this PowerPoint. Okay, so the document camera should be showing up. Is it true?
Yep.
Okay, so let's say that we started out trying to make O2 like this. So we start off with our typical oxygen, cobalt, oxygen, with the cobalt in the octahedral sites between the two oxygens. And then we put a lithium here on C. If we put a lithium on B, it would be in a tetrahedral site because it's right above the oxygen. So we're not going to do that. We could have put it on A, but we put it on C. And then the only place to put the next oxygen is on A, if this is going to be an octahedral site. And if you make the next layer have the same slope of the line between oxygen, cobalt, oxygen, like this, you end up like that. And then it's a 2-layer unit cell. So the next layer has to be in the same position as the first. And then you look and see what you're left with. There's no octahedral sites for lithium. You've got oxygen, oxygen right above each other. It's not an octahedral site at all. And if you draw it, it's actually a prism. It's a prismatic site like this. Okay. And these are not common in the lithium intercalation materials. You very rarely see the prismatic sites. But in sodium intercalation compounds of oxides, you often see prismatic sites for sodium because it's just bigger and it likes to have a bigger hole to fit in. Okay. So there's only one way to make O2 lithium cobalt oxide, it turns out, and it's the way that I showed you. It's kind of cool. Any questions about that? All right. So now I want to go back to the PowerPoint again. There it is. So you have all this, and I've emailed this to you. You can look at it and think about it. But this is really quite amazing. And there's a good story about this particular thing. So when you take lithium cobalt oxide and charge it up to about 4.55 volts versus lithium metal, it forms this very bizarre structure where about 12% of the original amount of lithium remains. And what you will find out is some of the spaces between the cobalt oxygen sheets have no lithium at all. They're empty. And some of the places between every second one between the cobalt oxygen sheets has some lithium. About 25%, 1/4 filled. 1/4 of the lithium sites are filled randomly with lithium. So it goes 1/4 filled, empty, 1/4 filled, empty, 1/4 filled, empty. It's quite a strange structure. And it's called O6 because the lithium is in octahedral sites and it's a 6-layer repeating itself. And what's really cool about this structure is that Gerd Cedar, a very famous theorist, and his students predicted it would form before it was experimentally observed. And then Xiaowei Chen, who was a graduate student of mine, and we found this structure, and we were quite impressed that the theory predicted that it should form before the experiment confirmed that it did. It's really very cool. But I want to just spend a moment describing this structure to you with my document camera because it's really cool. And given the time, it may be best to start with this next day. Let me just see what the next slide is after this. Okay, then we move on to different structures. Yeah, I'll start with this next day, and then we'll move on to the spinel structure and the lithium iron phosphate structure. So I believe at the end of Wednesday, we'll have finished this positive electromaterial structure portion. And then on Friday, we'll start on the negative electromaterial stuff, which will take quite a bit longer. There's a lot more complications involved there. So I'll put your homework together, your first homework together, which you should be able to do without any trouble after Wednesday. And I'll email it to you sometime on Wednesday or tomorrow. Okay, any questions about today? Don't know if anybody's speaking. Maybe not.
I have one question.
Sure.
So are there any other, remarkable examples where theory has predicted something before experiment that you can think of now?
I know that there's been some examples where theory has predicted some lithium carbonophosphates that could be formed. No one had ever thought to make carbonophosphates. And then anyway, Gerd Cedar and his bunch came along and said, you should be able to make these materials, and they should have a voltage curve that looks like this. And sure enough, people synthesized them, and the voltage curve was close to that which was predicted. So there has been situations where totally unknown materials have been predicted that have then been synthesized. There's been plenty of totally unknown materials predicted that could never be synthesized too. All right, sounds like a good place to stop, and we'll talk again on Wednesday. Goodbye.
Thank
Bye.
you.
Thank
Bye.
you.
Thank you. Bye.